That is because there's only one table for the system, and if you don't use hash table, you have to allocate really large storage for this process table. So we want to make it smaller by hashing. And there is the PID max variable that tells you the maximum process ID, so that there's a limit to how many processes can exist at one time. But how this relates to the file table? File table is similar in that file descriptor is mapped to the file information, just like the process table. But the difference is that there's one file table per process instead of this process table where there's global table. So we can simplify implementation a bit by not hashing. So since there's a file table per process, you don't have to hash the table. So you just use the file descriptor as an index. So this is the what's given to you in the file.h, and you need to change this variable to whatever you want. And also this table is a member of a thread, so this table is per process. So if you get your current thread, you can get the file table for that process by using that variable. And as I said, you don't have to hash the table, so this index to this table will be file descriptor. And there's a limit to number of files that a process can create, which is open max, shown here. And what should go into this file table? If you look into the assignment, if you have looked into the assignment already, there is a simple implementation for the console. So right now, sysread and syswrite uses, there's a code for console only, so you can read from the console and write to the console. And it's using EFS open to get the vnode for the console. And if you look into the code further, you just vup read and vup write, all capital letters, and they are vnode operations. And all of them accept the vnode as an argument. So you need, as I told you last week, you need a way of mapping file descriptor to the vnode, because all the vnode operations like vup read and vup write uses vnode inside. So file table can be thought of as mapping file descriptor to the vnode. And after you get the file descriptor from sysopen, for future operations, you can find the vnode from the file table, implement it, and pass it to the operations to implement the other system calls that we do. Questions for these here? Have you started, Simon?
Yeah. So the other thing that put into like abstract for the file was as well like flags, or are they stored in the heap, or I put them into the.
I'm gonna talk about it, but vnode shouldn't be changed.
Yeah. Okay.
Yeah. So everything else that you need should go into the software.
Reference counts and stuff like that.
Right, I'm going to talk about it too. Okay, so this is the simplified simplified version of file table, but it lacks many things. If you only take count of B node, then you'll hit a point where you cannot figure out if the file is open for read or write, or up to where in the file you have read or write written, so you don't know the offset to the file. So you need some way of remembering these as well in the file table. And also the sysopen system call is implemented for you, but file open function is not. And basically what you have to do is call BFS open on the path of the file and get a B node and then store it into the file table. And you can imagine if the file table looks like that, you can just assign a B node to the first entry of this table and return the index of that. And for future, you can just refer to this table. But it's too simple because, as I told you, there are more information you need to keep track of to make the file operations work, such as this open flag, which tells you if it's open for read only or write only or read write mode, and the read write calls in the OS 161 do not accept the offset as an argument. So unless you change the offset using LSIG system call, read and write just continues from the last position. Sorry.
What was that? Read and write doesn't accept what?
Doesn't accept the offset as an argument, right? Like if you look at it, read accepts file descriptor and the buffer and the length of the buffer, and that's it. Okay?
Yeah.
So there's no offset here.
How much you want to read now?
I mean, from where you want to read.
Okay, yeah, but that is, I mean, okay,
Yeah.
but that offset will be stored somewhere.
Yeah, it's stored somewhere in the OS, and it's assumed that unless you specify LSIG, you can change offset. You can change where you want to read or write next time. Unless you do that, then read or write just continues from the last point you left off. So you need to keep track of that offset. So you need to package about all these flags and the offset and other things. And tut1337 system call. It can also introduce additional problem for you because let's say you use tut1337 and everybody knows tut1337 system call. Yeah. So basically, you create an alias for the file that you open. So if you open the file and the descriptor is 3, let's say, then you want to use that file with another descriptor. Then you call tut1337 and it duplicates that descriptor. So descriptor 3 and 4 can point to the same file, for example. In that case, if multiple file descriptors point to the same file, you shouldn't close the file if one of the file descriptors is closed. Right? To do that, you need to keep track of how many file descriptors point to the file, and you need to keep track of how many of them are closed, so that at the last moment when every file descriptor is closed from the file, then you can close the file. And you can do this as a reference counting. So you need to keep track of reference counting for the files too. Yeah.
Like on the forum, she said something about blocking and that, but as the
Blocking?
yeah, she said you have to think about it if you have to work, but I was like surprised because it's like one thread per process, so it shouldn't we shouldn't worry about that.
So lock the file table or?
No, she said something, I'm not sure if she just said that to computers, but anyway, like, yeah, she said something about locking in that too, because I mean, if the process could be multi-threaded, that makes sense, because you could have multiple file descriptors pointing to the same file, so you would have to do some locking mechanism there.
That would be because of the, see, like the Arduino is global in the US.
Yeah.
Yeah. So,
Arduino is global, but for example, LC, for example, if you change the offset, for example, and you have two file descriptors, and then there will be two threads that change the offset at the same time, that would be protocol, but as we have one thread per process, that shouldn't.
yeah. I'm not sure. But, yeah, I'm not sure. Well, actually, like, where did you get the idea of this?
No, I wasn't sure, because she just like,
I mean,
somebody asked something on the forum and she wrote something in the end. She wrote, "You have to think about logging in this case." So I wasn't sure. There was a question about that too. But in my opinion, we don't need to log anything because there's one thread per process. So
I'm sure you guys will know.
well, that was in the last assignment. So
Okay. I'm not sure.
yeah.
Okay. I'll continue. As I said, we need to keep track of reference. Denote is a global representation, so if you open the same file in multiple process, you will get the same denote. Like denote, like virtual, like VFS itself internally also keeps track of the reference counting. Because as on the last point, it needs to know when to free the denote actually. So even if you call VFS close, if multiple processes open the files, then you cannot just post it. You cannot just say delete the denote. You have to keep track until the no process points to the denote, then you can delete it. But this is already done inside the VFS. This vnref count, it's part of the denote struct. It keeps track of the references whenever the file is open, and it only frees the memory when the count goes to 0. Also, denote keeps track of the open counting. It increases when a file is opened and decrements when the file is closed. This is used, so this of last close, what it does is it f-syncs the file system. So what it does is, for all the changes that has to be made, it flushes that to the disk, and it only does that if no process is holding the denote at the time. But if that's the case, can log2 be handled by opening the file So to create a duplicate file descriptor, can you just open the file again? And the answer is no, because VFS Open accepts the file path, but the file path can be changed before you call the doc2. So if you just use VFS Open and the file path has been already changed, like moving it to another directory, then the VFS Open will fail. So you cannot just use that, and you need to think of another way. Questions? So for the counting of dnode, like references and open counting, to keep track of when to fsync or when to delete the dnode, you don't have to really care about because it's already there for you. But for doc2, you need to keep track of reference counting because you need to make sure when to call VFS post. So it's like two levels. So even if you call VFS post, internally VFS file system keeps track of how many times the file has to be opened and closed. So there's a chance VFS post will only document the reference count for the dnode and do not. But on your process file table, if you did doc2 and old file descriptor and new file descriptor, and these two file descriptors point to the same file, you don't want to call VFS post 2 times on these because one of them hasn't been opened by VFS Open, right? If you call VFS post on these guys once, and then there's a reference counting issue because you only opened it once. So the way to do is, as I told you, keep reference counting of how many file descriptors point to the dnode. And when all the file descriptors that point to the dnode closes, then you can call VFS post once only, and the VFS will do the reference counting underneath you. And that's the point of this. So is it clear? Question. So the reference counting from your point, from your file table, is to figure out when to call VFS post. But internally, many processes can also have the same file open, and internally it figures out for VFS post when to actually close the file. Let's say this function inside here actually closes the file and release the dnode. This is handled by the VFS layer by keeping track of its own reference counting. So the point for your reference counting for your file table is to figure out when to call VFS post because of the doc2 system call, which can have multiple file descriptors pointing to the same dnode.
So did in one process to actually call open device, do we also like keep track of that separately?
Same file?
Same process, calls open device.
Open twice on the same file.
Yeah.
Right.
Can we keep track of that as well as the stuff?
No, this reference count is different than that because if you open it twice, you need to close it twice. So what dog is different than in your case is that for dog, these file descriptors share everything. So the offsets are saying if you change offset on this guy's offset changes too. But in your case, each file descriptors link to different offsets. So if you read from one, the other file descriptor's offset doesn't change. So they're like separate, and we need to close them twice because we open them twice. So we don't need to keep track of it. Because they'll be mapped to different file descriptor anyways, right? From the file table. Okay. So that's all for the file table. So this is about the uniform I/O. It's used throughout the 7.4 valve operation functions, and it's used to move data from kernel to the user space or kernel to kernel space. But in this case, it's moving data from kernel to user space. If you look inside, it's using UI remove function to move the data. But internally, it uses copying inside. But it also keeps track of other things like the offset and how many bytes are left and from where you're transferring to and the read or write mode. So you should use this for the 7.4 because it does many more things than just copying. And the way to use it is, so UIO, it's a struct. It's a struct with fields. And the way to set it up is, there's a function called make user IO. It accepts this UIO and initializes it according to your need. And if you look at any of the functions in A4, there's an example of how to do that, so you can figure out by looking at it. As I said, the offset for the files opened are kept internally, and you need to keep track of it in your file table. And this UIO accepts the offset, so it knows from where to start the operation. So internally for read and write, since you're using UIO and there's a UI offset field, you need to set it to the offset that you are keeping in your file table, so that you don't have to start from the beginning, but start from where you left off. And the UIO res ID, it's a remaining number of bytes that has to be, that you want to be read or written. And you specify it to tell the UIO feature that, okay, read this much bytes or write that many bytes and stop there. But the UIO can return early. In that case, the UIO res ID will tell you, okay, how many bytes are left off, so you need to try again. And this make user UIO in the file syscalls will initialize the UIO struct. After that, you can call UIO move or the actual functions to make the read or write happen. This VO read and VO write, they all work on this UIO, and after they are done, the offset changes and the res ID changes. The offset changes because after you read or write n bytes, the offset moves by n bytes and tells you, okay, we stopped until here, so next time you should start from this offset. So after you get this offset, you should update your file table. Right? And the UIO res ID tells you how many bytes are remaining. If the operation is successful, then it should be 0, but in case it's not 0, it means there's some leftovers, and usually read and write just returns that number, how many bytes are read or how many bytes are written, and usually user application retries read and write again until they're all processed. So the point of this is, after you get the offset, make sure you update your file table number offset. Questions? There's a getter entry and abstract system call that you have to implement. I believe it's last system call you have to go second last. The directory gives you what's in the directory. Abstract tells you about the file information, and they are mostly implemented, but they depend on a VOP function that uses vnode as an argument. So you just have to make sure that you just find the vnode from your file table and call the appropriate VOP function to make them work. They are really short system calls. Yeah, here for the getter entry, it says just record the offset and returning the UIO. Don't worry about this. Okay, so this is the final point of this tutorial. It's about subdirectories in SFS. So you need to implement few functions. Questions? Such as SFS maker for making directory, and you can get a lot of things by reading SFS create, which creates a new file. You need to do similar things as in that function, but modify few fields when you're calling the functions there. For example, instead of creating a file, you need to tell it to create directory and stuff like that. And this SFS make object function, you can create a file or a directory. In your case, you will call this function called the directory, and it handles all the inode allocations, and it also makes vnode for the directory. The directory ops, what it means is like vnode can either be file and directory, and depending on the type, the operations that it can do can be different. So if you set the vnode as directory, then the ops pointer there, which points to all the operations that vnode can do, will only point to directory related operations. If it's a file vnode, then it will point to only file related operations. So we don't need to worry about if it's directory or file when you're calling these functions, because you can only call the functions that will work on your type. This SFS derivate creates new entries in the directory, and the link can be either directory or the file. So here are the steps that you need to do when you create create a directory. First, in the parent directory, you need to create a link to the subdirectory that you're creating. So, if this the parent directory content, if you're creating a subdirectory inside, so parent needs to have this directory entry in this table so that you can reference it as parent/sub later. So way to do is use this parallel function. Also in Linux and OS 161, there's always this dot and dot directories in every directory. So dot points to itself and dot points to the parent. So after you create the subdirectory entry, inside the subdirectory entry, you should create the dot which points to yourself. You should also create dot which points to the parent. Pointing meaning you should know the v node for the subdirectory and the parent directory. And you can also use the same function to do all these. After you do all these, then you can say you created the directory, because dot and dot always has to be in any directory, and you need to have a reference from parent to subdirectory and subdirectory to parent. And there's also this thing called link count, and it's used to figure out when you can actually delete the directory. So if there is some content in the directory, if you just remove dir, the Linux will say no, there's some content in the directory. So the way they do it is they count how many entries are in the directory by using the link count. So make sure you update the link count from all the parent and also of the subdirectory, because you're modifying two at the same time. Remove dir can be very similar to remove function. So if you reference that function, it will help you quite a lot. But the difference here is that when you're figuring out, so there's this SFS and entries, which tells you which represents how many entries there can be in the directory, and this n entries tells you number of entries that can be in the directory, not number of entries that are free in the directory or used in the directory. So what you have to do is look at each individual entries in the directory and figure out if its inode is equal to SFS no inode. That means that entry is not used. So if you look through all the entries and all of them are not used except for the dot and bottom, then it means there's nothing in the directory. Then you can remove the directory. After you do that, make sure you update the link count of the parent, the removed dir. You need to update with the parent because parent can have another entry beside this directory, so you need to keep track of the entries there. These are other functions you have to implement. Lookup gives you the node for the path that you've given. Look parent gives you the node for the parent of the path that you've given. And these work from the node that you provide. So they don't have to the path that you give doesn't have to start from the root directory. They could start from your current working directory, which is kept as the current working directory field in your thread.
So there are actually three cases. Either it starts with dot, either it starts with dot, or it starts with slash. The path.
If this starts with dot, then it doesn't hold anything.
Dot. Sometimes you type in dot for dot slash and then
to run something.
Yeah.
So dot means it's current directory. Dot means from your parent.
Yeah, so I don't know, should we handle that case dot? I mean, you can type dot and then go down.
You should handle this. Yeah. So if I remember right, how they work is from your current directory. So if you specify a path like dot and some dir and file, right? This function will think of this path starting from your current directory. So it will go to the parent of your current directory and starts to look for the dir in the parent, and then look for the file. And if the file is there, then it will return the dnode, otherwise error. So how you do is break out the path by slash, and as I said, if this is dir1 and dir2 and that's file 1, you have to find the dir1 first, which is a parent for you, and you have to find the dir, and you have to find the file.
Do we have to like handle special cases if we use create directories with spaces and stuff like that? Or?
I don't know if it works actually, because the way you find the directory is you just calling a function that can find something. So if that function can handle path with the spacing, then if it doesn't, then don't bother with us.
Okay.
And that function is SFS root once. So here, if you call this function and that function can find whatever in the path, it will return the dnode for you. Okay, so that's like very similar as this example. So if your current directory is here and you need to look for that path, then you break up the path by slash. So you first look for the dot using this look once function, and dot is a parent, so it will try to look for dir2. If it's there, you will return the dnode for that. And from there, you look for the dir21 with the same function, and keep doing it until you find the file, and return the dnode at the end for the lookup and lookup path. So you have to, one thing to note is as you are calling loop once multiple times, you need to keep track of it because it increases the reference count underneath. So all you care about is this last dnode. You need to make sure that the reference for these are decremented after you find the dnode. Okay. So this is another similar function you have to implement, and this accepts a dnode. returns the path, so it's opposite. So what you do is from the V node, actually I'm not sure if it can be any V node or your current V node, but let's say you want to find path of your current working directory, then what you do is you just have to walk up the tree until you reach the root. So what you do is just call the same function SFS loop once on the dot dot, and it will give you the V node. After you get the V node, there's a function called the SFS reader, I think, and I think using that you can get the name of the directory. So once you get the V node, you can convert that into a directory name. And after you do that, you use SFS loop once again from there, from that directory using dot dot to go up one more level. Keep doing this until you reach the root, and all the directory names that you got, you just combine them together to get the path. Still last one. So for the loop parent, since it's only interested in the parent, the final, so the ending part of the path doesn't have to exist. And have you started assignment?
Yeah, but I'm not there.
So yeah, I'm not there either. But have you tried like creating the volume? Yeah. So these you use them to choose which file system you want to visualize in the timeline. And what this is saying is that all these FSS functions only work with this, not the volume name. And the final point, continuous recursion, like these are candidates for recursion because they do the same thing all the time. But don't use recursion for these because a stack is very small, and if you have stack overflow in the kernel, you don't even know like what is going on. It's very hard to figure out. And that's it. Questions?
Okay, and she said this.